The Foundations of Geometry by David Hilbert.
Conclusion. The preceding work treats essentially the problems of Euclidean geometry only. That is to say, it is a discussion of the questions which present themselves when we admit the validity of the axiom of parallels. It is nonetheless important to discuss the principles and the fundamental theorems when we disregard the axiom of parallels. We have thus excluded from our study the important question as to whether it is possible to construct a geometry in a logical manner without introducing the notion of the plane and the straight line by means of only points as elements, making use of the idea of groups of transformations or employing the idea of distance. This last question has recently been the subject of considerable study due to the fundamental and prolific works of Sophus Lie. However, for the complete elucidation of this question, it would be well to divide into several parts the axioms of Lie, that space is a numerical multiplicity. First of all, it would seem to me desirable to discuss thoroughly the hypothesis of Lie, that functions which produce transformations are not only continuous, but may also be differentiated. As to myself, it does not seem to me probable that the geometrical axioms included in the condition for the possibility of differentiation are all necessary. In the treatment of the questions of this character, I believe the methods and the principles employed in the preceding work will be of value. As an example, let me call attention to the investigation undertaken at my suggestion by Mr. Dehn, and which has already appeared. In this article, he has discussed the known theorems of Legendre concerning the sum of angles of a triangle, in the demonstration of which the geometer made use of the idea of continuity. The investigation of Mr. Dehn rests upon the axioms of connection, of order, and of congruence, that is to say, upon the axioms of groups 1, 2, and 4. However, the axiom of parallels and the axiom of Archimedes are excluded. Moreover, the axioms of order are stated in a more general manner than in the present work, and in substance as follows. Among 4 points A, B, C, and D of a straight line, there are always 2, for example, AC, which are separated from the other 2 and conversely. 5 points A, B, C, D, and E upon a straight line may always be so arranged that AC shall be separated from BE and from BD. Consequently, AD are always separated from BE and from CE, etc. The elliptic geometry of Riemann, which we have not considered in the present work, is in this way not necessarily excluded. Upon the basis of the axioms of connection, order, and congruence, it is to say the axioms 1, 2, and 4, we may introduce, in the well-known manner, the elements called ideal points, ideal straight lines, and ideal planes. Having done this, Mr. Dehn demonstrated the following theorem. If, with the exception of the straight line T and the points lying upon it, we regard all of the straight lines and all of the points, ideal or real, of a plane as elements of a new geometry, we may then define a new congruence so that all of the axioms of connection, order, and congruence, as well as the axiom of Euclid, shall be fulfilled. In this new geometry, the straight line T takes the place of the straight line at infinity. This Euclidean geometry, superimposed upon the non-Euclidean plane, may be called a pseudo-geometry, and the new kind of congruence a pseudo-congruence. By the aid of the preceding theorem, we may now introduce an algebra of segments relating to the plane, and depending upon the developments made in section 15, this algebra of segments permits the demonstration of the following important theorem. If in any triangle whatever, the sum of the angles is greater than, equal to, or less than 2 right angles, then the same is true for all triangles. The case where the sum of the angles is equal to 2 right angles gives the well-known theorem of Legendre. However, in his demonstration, Legendre makes use of continuity. Mr. Dehn then discusses the connection between the three different hypotheses relative to the sum of the angles and the three hypotheses relative to parallels. He arrives in this manner at the following remarkable propositions. Upon the hypothesis that through a given point we may draw an infinity of lines parallel to a given straight line, it does not follow, when we exclude the axiom of Archimedes, that the sum of the angles of a triangle is less than two right angles. But on the contrary, this sum may be A, greater than two right angles, or B, equal to two right angles. In order to demonstrate part A of this theorem, Mr. Dehn constructs a geometry where we may draw through a point an infinity of lines parallel to a given straight line, and where, moreover, all of the theorems of Riemann's elliptic geometry are valid. This geometry may be called non-Legendrian, for it is in contradiction with that theorem of Legendre, by virtue of which the sum of the angles of a triangle is never greater than two right angles. From the existence of this non-Legendrian geometry, it follows at once that it is impossible to demonstrate the theorem of Legendre just mentioned without employing the axiom of Archimedes, and in fact, Legendre made use of continuity in his demonstration of this theorem. For the demonstration of case B, Mr. Dehn constructs a geometry where the axiom of parallels does not hold, but where, nevertheless, all the theorems of Euclidean geometry are valid. Then we have the sum of the angles of a triangle equal to two right angles. There exist also similar triangles, and the extremities of the perpendiculars having the same length and their bases upon a straight line all lie upon the same straight line, etc. The existence of this geometry shows that, if we regard the axiom of Archimedes, the axiom of parallels cannot be replaced by any of the propositions which we usually regard as equivalent to it. This new geometry may be called a semi-Euclidean geometry. As in the case of the non-Legendrian geometry, it is clear that the semi-Euclidean geometry is at the same time a non-Archimedean geometry. Mr. Dehn finally arrives at the following surprising theorem. Upon the hypothesis that there exists no parallel, it follows that the sum of the angles of a triangle is greater than two right angles. This theorem shows that with respect to the axiom of Archimedes, the two non-Euclidean hypotheses concerning parallels acts very differently. We may combine the preceding results in the following table. Column 1. The sum of the angles of a triangle is greater than two right angles, less than two right angles, equal to two right angles. Under the heading, through a given point, we may draw, column 2, no parallels to a straight line. Riemann's elliptic geometry. This case is impossible. This case is impossible. Column 3, one parallel to a straight line. This case is impossible. Euclidean parabolic geometry. This case is impossible. Column 4, an infinity of parallels to a straight line. Non-Legendrian geometry. Semi-Euclidean geometry. Geometry of Lobachevsky, hyperbolic. However, as I have already remarked, the present work is rather a critical investigation of the principles of Euclidean geometry. In this investigation, we have taken as a guide the following fundamental principle, viz., to make the discussion of each question of such a character as to examine at the same time whether or not it is possible to answer this question by following out a previously determined method and by employing certain limited means. This fundamental rule seems to me to contain a general law and to conform to the nature of things. In fact, whenever, in our mathematical investigations, we encounter a problem or suspect the existence of a theorem, our reason is satisfied only when we possess a complete solution of the problem or a rigorous demonstration of the theorem, or indeed when we see clearly the reason of the impossibility of the success and consequently the necessity of failure. Thus, in the modern mathematics, the question of the impossibility of solution of certain problems plays an important role. and the attempts made to answer such questions have often been the occasion of discovering new and fruitful fields of research. We recall in this connection the demonstration by Abel of the impossibility of solving an equation of the fifth degree by means of radicals, as also the discovery of the impossibility of demonstrating the axiom of parallels, and finally the theorems of Hermite and Lindemann concerning the impossibility of constructing by algebraic means the numbers e and pi. This fundamental principle, which we ought to bear in mind when we come to discuss the principles underlying the impossibility of demonstrations, is intimately connected with the condition for the purity of methods in demonstration, which in recent times have been considered of the highest importance by many mathematicians. The foundation of this condition is nothing else than a subjective conception of the fundamental principle given above. In fact, the preceding geometrical study attempts in general to explain what are the axioms, hypotheses, or means necessary to the demonstration of a truth of elementary geometry. And it only remains now for us to judge from the point of view in which we place ourselves as to what are the methods of demonstration which we should prefer.
The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Renholt. Programming and illustrations by Jim Renholt. 2019. Portrait of David Hilbert by Rita Ray Renholt. Thank you for listening.